Hi, my name is Nick Borson, and this video is part two of a series about pointers, which is primarily a feature of C and C++. But this series is geared not so much to C programmers or C++ programmers as to programmers in any language who want to better understand how memory works and how memory management works, because C gives you a very low-level perspective on that, and other languages sort of build on top of those concepts, but had their own more stronger safety guarantees and so on. Now, if you have not watched the previous video, I will include a link to it in the description. But this is kind of the roadmap that we followed in the previous video. I first talked about what pointers are, that C is the reason that we might want to care about pointers, even if we're not programming in C, just to understand how memory works. And in the previous video, I gave some examples of using pointers to refer to arrays and work with arrays and pass arrays to functions, for example, by passing them by their address via a pointer. In this video, I'm going to talk a little bit more about pointers as a way of working with dynamic memory, of memory that's allocated on the heap. And I'll also allude a little bit to different data structures involving pointers where you would need to allocate memory on the heap. And the example, pointers, this can be things like graph data, linked data structures like trees or linked lists, things like that. But it could also be, in the example I'm going to show, I'm just going to have read a text file into an array of strings. And finally, I'll talk a little bit more about the risks and shortcomings of pointers and how other languages mitigate those shortcomings. Now, in this video, I'm going to focus especially on the concept of lifetime, or as it's referred to in the C and C++ standards, storage duration. Any object in C or C++ has a storage duration which is either automatic, static, or dynamic. An object in this case really just means a chunk of memory that can be used to hold some value or values of some type. So automatic storage duration is what for local variables. These are stored on the stack, that is just in temporary storage that goes away when a function returns. And the lifetime of the variable, therefore, is tied to the flow of control. As the flow of control leaves a particular block or leaves a function, then the storage allocated to that variable automatically goes away because that stack frame for that function is popped off the stack. Another kind of storage duration is static, and this applies both to global variables as well as local variables that are marked with the static keyword. And static storage means that the variable or the storage for that variable lives for the lifetime of the program. So of course that makes sense for global variables because you would expect something that's global to the program to exist for the lifetime of the program. And finally, what's a bit more involved is dynamic storage, or things that are allocated on the heap, or in the C and C++ standards, this is referred to as the free store. The heap is a place where you can allocate memory over time as the program runs, and then you can free up that memory. And in C and C++, the lifetime of memory of objects on the heap is explicitly managed by the program. You can allocate the memory, and then you're responsible for freeing the memory. This is in contrast to, for example, Java or C#, where there is something called a garbage collector that will automatically clean up free memory that is no longer referenced by your program. In C, you can create a pointer to any object, regardless of its storage duration, by just taking the address of that object. And the pointer doesn't really capture anything about the storage duration of the object. It doesn't know what the storage duration of the object is. So this creates the potential that you can have what's called a dangling pointer, where the pointer itself outlives the object that it points to. So let's illustrate how that can happen with a little simple program here. So and I'm going to kind of show visually what's happening with the local storage as we run through this program. This program has two functions. It has a read line function and then the main function starting on line 10. The main function is the program entry point. This is where the code starts running when your program is launched. So when the flow of control enters the main function, the a stack frame is created for the main function that contains all of its local state, including its local variables. And in that main function, we have a local variable called line, defined on line 13. Initially, we just reserved space for line. We haven't actually executed the initializer for it, so it just contains garbage data. Then on line 13, we actually call the readLine function, and we assign its return value to the line variable. So when we enter the readLine function on line 3, another stack frame is created and pushed on top of the stack that contains all the local variables for the readLine function. It also contains any other local state needed by that the compiler needs, such as the return address. So readLine has one local variable called buffer, which is an array of 80 characters. This is defined on line 5. So visually, I've just shown this as an array. The name buffer is bound to this array of characters. And I put in some dotted lines because I didn't want to show 80 little boxes on the screen. On line 6, we call a function, a standard library function called fgetS, which reads a line of text from a stream. We pass the buffer. The fgetS takes a pointer and a size, so we pass the buffer, which decays from an array to a pointer to its first element. And then we pass the size and bytes of the buffer, which we can get its compile time by using the size of operator. And finally, we pass the stream that we're reading from, which is the standard input stream, which is simply we're reading from the console. We're reading user input here. So let's say I type the word hello and press enter. Then the fgetS function is going to store those characters, the HELLO, and a new line character, followed by a null terminator, that is character code 0, in our buffer. And then it returns. And so far, so good, because the buffer is a local variable declared on line 5, so it has automatic storage duration. But fgetS uses the buffer and returns, and the buffer is still in scope for that whole time, so there's no problem with lifetime there. But then on line 7, we return the buffer as the return value of this function. And on line 13, that return value gets assigned to the local variable line in main. So here we now see that the line variable in the main stack frame points to the storage that was the buffer in the readLine stack frame. But as soon as we returned from readLine, that whole stack frame went away. So line is now pointing to storage that is no longer allocated. The data might still be there temporarily, but it's no longer actually allocated. It can anytime be overwritten by something else. And in fact, on line 14, when we call fputS, it's going to create its own stack frame and quite likely overwrite the contents of our buffer. So it's totally invalid to be able to refer to that storage. So that's an example of how a dangling pointer can exist. One way that can happen is by returning a pointer to a local variable. So how can we mitigate that problem so we no longer have a dangling pointer? Well, one option is to use a static buffer. So this program is exactly the same as the one we just looked at, except that on line 5 we see that the buffer variable is defined with a static keyword. That means that this buffer has static storage duration. It exists for the lifetime of the program. For all intents and purposes, it's the same as if buffer is a global variable. The only difference from a global variable is that it's only visible from within the readLine function. So this way we avoid undefined behavior, because when readLine returns, that pointer, or that buffer still exists. However, it's not really an ideal solution in this case, because the one issue is that static buffer always exists whether it's used or not. So we're kind of wasting space potentially by creating storage that's always dedicated whether or not we're actually using it at the time. But a more serious problem is that all calls to readLine use that same buffer. So if we call readLine once and read a line of text and return a pointer to it, then that's fine. But what happens if we call readLine a second time? Well, we're going to get back that same pointer, and that buffer is going to be overwritten by the new data we read. So consider, for example, if here we have modified the main function to call readLine twice. So first we say enter your first character, or sorry, enter your first name. We call readLine, store a pointer to the first name. Then we call enter your last name on line 15. We call readLine again, and we store a pointer to the last name. But in fact, first name and last name are both pointing to that same buffer because it's the static buffer. So when we make that call on line 16, we're actually reading the second string. That second string is overwriting the buffer that was also used for the first string. So when we print on line 18, when we print hello, first name, last name, we're actually just going to print the last name twice. Not really what we were intending in this case. So there's kind of a hidden gotcha there from using a static buffer. That there's this hidden dependency. You might think readLine is just reading a new line of text, but it's really overriding some global storage, some static storage, which kind of can lead to some issues. Other issues with static storage is that it's not thread safe for multiple threads to be writing to the same static storage unless it's guarded by some kind of synchronization. So there are a lot of issues with the static data that unless it's just used for constants or something like that. We've seen we've considered automatic and static storage duration. Let's now consider the third possibility, which is dynamic. So here's a new version of our readLine function that allocates the buffer on the heap. So each call to readLine is going to return a new buffer that has been allocated on the heap, and it reads a line of text into that buffer. So on line 7, on line 6, we specify the size of the buffer we're going to allocate. On line 7, we allocate that buffer by calling the malloc function, which is for memory allocation. And it takes a parameter, which is the size in bytes of the heap of the memory we're going to allocate. And that function is declared in the stdlib.h header. So we've included that header file on line 2 of our program. Now, malloc, because you're allocating memory at runtime from the heap, that allocation can fail if you run out of memory. So in which case malloc returns a special pointer value called null, which is a pointer that doesn't point to anything. So on line 8, we have to add a runtime check, to make sure that the buffer is in fact not null, that we actually succeeded in allocating the memory. If that's the case, then we go ahead and call fgetS just like we did in the other examples. We pass the pointer to the buffer, we pass the size of the buffer, we pass the stream we're reading from, which is standard input, the console input, and fgetS will just read into the buffer the same as before, and then on line 12 we return that pointer. Of course, depending on whether we took that if case, the pointer, we may be returning null because the malloc failed, or we may be returning a pointer to a buffer into which we've read some text. So let's look at how we call our updated readLine function from main. So here's our main function. Again, we output a message, and then we call readLine, and we assign the returned pointer to a local variable. So that's on line 18. So the line variable now points to a buffer that we allocated on the heap. Now, again, because readLine now can potentially fail, we have to check that the pointer is not null. So we have a null check on line 19. If we have a valid pointer, then on line 21 we output the string, and on line 22 we then have to free the buffer. So that's another new thing about dynamic storage duration. If we allocate memory using malloc, we're ultimately responsible for freeing it using free. So there's this is kind of part of the implied contract then for our new readLine function. ReadLine returns a pointer to newly allocated storage on the heap, and the caller then is responsible for freeing that pointer. So having dynamic storage gives us some advantages because each call to readLine is going to return a new pointer, so we can read multiple lines of text and have multiple lines of text all stored in memory at the same time because each call will allocate additional storage. But it does impose some additional bookkeeping costs on the caller because the caller has to be able to deal with the potential of runtime errors, and the caller is also responsible for freeing up that storage. All right, let's consider a more elaborate version of our readLine function. So one limitation of the previous version is that we always allocated a fixed size buffer. So what happens if the line of text that we wanted to read exceeded the length of that buffer? Well, one advantage of dynamic memory allocation, in addition to having control over the lifetime, is that we can also allocate buffers of varying size at runtime instead of having to declare at compile time what the size of an array is. So in this version of the function, we're going to read the text, and then if the entire line didn't fit into our initial buffer, we can reallocate the buffer to be bigger. So I've added a block comment at the top of the function to explain a little bit more about what it does. It returns a null terminated string. Again, this is kind of the conventional C way of indicating where a string ends, is just to stick a null character on the end. And it specifies that the caller is responsible for freeing the return pointer. Okay, so on line 17 and 18, we define two new local variables called capacity and length. So I've defined capacity to mean this is the size in bytes of the buffer that we've allocated. And length is the number of characters, not including the terminating null character. So it's the length of the string that we've read into the buffer so far. Then on line 21, we allocate the buffer with our initial capacity. And I've defined the capacity to be fairly small, just 32 characters. So we have a buffer that is of size 32 or 32 bytes. Char is, one char is equal to 1 byte in C. And of course, we again have to do a null check as before. So if allocation failed, we return null. Now we enter a loop. So this is different than before because we might have to do more than one read if we have to read, if we have to grow the buffer. So for each iteration of the loop, now we may already, so our invariants here, there's this concept of an invariant in programming where these are things that are always true. So our invariants are that capacity is always the size in bytes of the buffer, and length is always the number of characters in the buffer so far. So for each iteration of the loop, those two invariants are always expected to hold when we enter the loop body. So the buffer initially might not be empty. We might have some data already in the buffer from the previous iteration. So on line 33, we're expecting that there's still some extra capacity in the buffer, and there may already be some text in the buffer, but there is always some additional capacity. So we read into the buffer by passing the pointer to one past the last character, that is buffer plus length. So one past the last character already in the buffer. So we're pointing to the free space at the end of the buffer. And then we pass the size of this free space by just subtracting length from capacity. And again, we pass the input. By the way, in this version of the function, I've specified, instead of always reading from std_in, I'm passing the input stream as a parameter. Okay, so on line 33, we read into the buffer. If that read fails, then fgetus returns null, and we free the buffer and return null. And then we've successfully read from the buffer, so we have to determine how many characters do we read. Well, we can use the strlen function, which is in the string header, string.h. So I've included string.h on line 3. So we use the strlen function to scan for that null character, and we scan starting with the last character that we had read before. So we scan starting with buffer plus length, and we see how many more characters we have after that, and we add that to length. So length is now the updated length. And then we check to see if we reach the end of the line. So the fgetus function, if it's read the entire line, then it's always going to append, then the last character read is going to be the new line character. But if we filled up the whole buffer without finding a new line, then the last character is not going to be a new line character. So this is how we detect on line 44 if we've reached the end of a line or not. We check whether we have a non-zero length, and the last character, the character at length -1, is a new line character. If it is a new line character, then we replace the new line character with the null terminator on line 47. So we're basically chopping off that new line character, and we fall out of the loop. Otherwise, on line 52, if we fall through here, if we haven't hit that break statement, so we can continue execution. That means we haven't found the new line character. what that should mean is that, so what one possibility for that is we've reached the end of the file. So we check to see if this is calling a standard function again to check if we've reached the end of the input. So if we have, then we've reached the end of file. So we could have reached end of file, or we could have reached the end of the line, or we could have reached the end of the file. Either way, we're just going to fall out of the loop because we have no more text to read. Finally, that then if we haven't reached the end of the file and we haven't reached the end of the line, then we need to reallocate our buffer to make it bigger. So now we compute our new capacity. So capacity, again, remember, is what we call the size in bytes of our buffer. So we just double the capacity each time. So we compute the new capacity that we're going to allocate. And on line 60, I do an integer overflow check. So what can happen here is that an integer can only, any integer value, or any kind of number really in a program, can only hold values so big. So let's say an integer is 32 bits. The largest possible positive integer you can store in an int, if it's 32 bits, it would be 2 to the 31, which is about 2 billion. If you get bigger than that, it's going to overflow to a negative number. So to check for an integer overflow, I just make sure that the new capacity is in fact greater than the original capacity before we doubled it. If the new capacity is less than or equal to the original capacity, then we know we've encountered an integer overflow, and therefore we treat that as an error. We free the buffer and return null. So that's how we're indicating an error from this function. It's important to check for integer overflow in this case. This is just one example of where doing this kind of manual memory management correctly in a language like C is requires some care, because if we didn't do an integer overflow, that could lead to undefined behavior. We might end up allocating a buffer that is in fact smaller or than the original buffer, and it could lead to errors down the line and what have you. So on line 68, then we actually reallocate the buffer. So we call another function called realloc. It takes the original buffer, the new capacity, the new size in bytes, and that will either grow the additional storage in place, or it will allocate new storage, copy the previous data from the previous buffer to the new buffer, and free the old buffer. And in either case, it returns to the new pointer. Now, if realloc failed, then it's going to return null. Now, when that happens, that means that realloc essentially didn't do anything. So the old buffer still exists in that case. So we have to free the old buffer and return null. That's how we indicate our failed allocation. Finally, if we got through all that, we've allocated a bigger buffer, we save we update buffer to point to the new location, we update capacity to indicate its new capacity, and then we're again going to go back to the next iteration of the loop where we read more data into the free space at the end of our buffer. Finally, when we get to our end of file, or excuse me, when we get to our end of line here, or when we get to our end of file, we'll fall out of the loop. And at that point, we've successfully read an entire line of text, and so we return that to the caller. So here, this demonstrates how we might call this function. So we have enter your first name. We read the first name by calling readLine. We have to do a null check because, again, it can fail. We say enter your second name, read the last name, or enter your last name, read the last name using readLine. Again, each of these calls is going to allocate a new buffer. So first name points to its own buffer on the heap. Last name points to a separate buffer on the heap. Each of those we do a null check. And if all that succeeded, we say hello, first name, last name, and we're good. Then we free last name if we successfully allocate it, and free first name if we successfully allocated it. So again, the caller is responsible for cleaning up storage. So this kind of illustrates a little bit, how it's important to be able to write. To do this kind of nitty-gritty memory management in a language like C can be tricky. So it's important to write to encapsulate this kind of logic in helper functions that handle that nitty-gritty for you. But it does involve having to check for errors. It involves the caller having to clean up, and involves some care. All right, let's finally build on this by creating one further example. And in this example, we're going to, again in C, we're going to read an entire text file into memory. And to do that, we're going to define a structure that represents the contents of a text file, essentially as an array of lines of text. And this will introduce a new concept, which is a pointer to a pointer. So our text file structure is going to have three members. It's going to have a lines member, which is a pointer to an array of pointers. And each of those pointers will then point to a null terminated string, which is allocated on the heap. So both the array of pointers itself is allocated on the heap, and then each of the pointers in that array points to another heap allocated object, as shown in the diagram here. So lines points to a heap allocated array, and each element of that heap allocated array is a pointer to a heap allocated character array. The other two members of the structure are size, which is the number of lines, and capacity, which is the number of the maximum size, the maximum the size can be without having to reallocate the array. So it's the capacity, the allocated size of the array, if you will. Size being the actual number of lines on the array, how much of the array is full, and capacity being how big the allocated space is. So let's go ahead and look at the code for doing this. Here's our updated program. Again, we have our readLine function, which is exactly the same as before. It will read a single line of text and return a pointer to a newly allocated heap object that contains that text as a null terminated string. Here then is our text file structure. So we use the struct keyword in C. We're defining a structure called text file, so struct text file. The curly braces, inside the curly braces are the members of that structure. So we have lines is our pointer. And here we have, notice we have two stars because lines is a pointer to a pointer. So the type of star lines is char star. So in other words, when you dereference lines, you get a array of character, you get a pointer to a character. So it's a pointer to a pointer of characters. Then we have our size and capacity, and both of these are declared as of type size t, which is an unsigned integral type that can hold that can represent the largest possible memory object, the size of the largest possible memory object. Now this type def bit here is because of the peculiarity of C, which is that when you say struct text file, this is true in C, but not in C++, by the way. When you say struct text file, that name text file is kind of in a separate namespace that's specifically for structures. So anytime you want to refer to this, you have to say, you can't just say text file to refer to that type. You have to say struct text file. So that's kind of inconvenient. So it's common to use the type def, which just introduces an alias or another name. And so we're just saying type the name text file all by itself is another name for struct text file. That way we can then elsewhere in the program refer to just text file instead of having to write struct text file all the time. Okay, so I defined a couple of functions that are specifically for doing things with text file objects. So here I have a text file initialize function. So the idea here is that I just want to encapsulate what is the logic for, given a text file structure, how do we put it as an initial state? And we'll say its initial state is going to be that the lines pointer is null, the size and capacity are both 0. So it doesn't contain any, doesn't point to any storage. Obviously, if it doesn't point to any storage, there aren't any strings in it, and there's no storage allocated. Then we have the opposite of initialize is destroy. So when we're done with the text file and we want to actually free all resources from it, we call this text file destroy method. Now text file points to a heap allocated array, and each element in that heap allocated array is a pointer to a heap allocated array of characters. So to free everything, we have to loop over all the elements of the array up to but not including size, and then free each of those pointers. So if you remember back to our diagram, this is freeing the buffers for each of the strings. Then we call free. So here we have lines subscript I. We're grabbing one of the pointers out of the array. That's a pointer to a string. and we're going to pass that to the free method, free function. Then we free the array itself. So we pass the actual raw pointer to the pointer to the array of pointers, and we free that object as well. And then finally, we just to ensure that text file is still in a valid state, we just set everything back to its initial state where it is null and a 0. Now here's another helper method, which I'm calling text file grow capacity. So what this is doing is it makes the allocated size of the text file bigger. This is very similar to what we did in our read line function, where we wanted to grow our array of characters. Here we want to grow our array of pointers. So we start with whatever the current capacity is, we double it. Or if the current capacity, so if the current capacity is non-zero, we compute the new capacity by doubling it. If current capacity is 0, we just set the new capacity to 16. So the first time we do an allocation, we're going to allocate 16 pointers. Each subsequent time, if we need to increase the capacity, we'll just double it. Here we do an integer overflow check. Again, sort of like we did in our read file function, or read line function. So if the new capacity is less than or equal to the old capacity, we know that this multiplication overflowed, right? And furthermore, down below on line 127, when we call realloc, we have to multiply, in order to get a size in bytes, we have to multiply the capacity by the size of a char star pointer. So we want to make sure that multiplication doesn't overflow, so here we do an overflow check there. So if we got an integer overflow, we just leave the text file in its existing state, and we return 0 to mean an error. So this function returns 1 if successful or 0 on error. Here's where we do the reallocation. So we pass the old array, the pointer to the old array, and we pass the new capacity in bytes. So the capacity member variable represents the number of pointers. To convert that to a number of bytes, we multiply that number by the size of a char star pointer. Realloc will take the existing buffer and either grow it in place or allocate a new one and copy the old data. And it returns a pointer to the new buffer, which may be the same as the existing buffer. If it fails, then the old buffer is still valid. We just return 0. Text file, we leave text file in its existing state. We don't change anything. If it succeeds, then P is going to point to the new address of the buffer. And so we update the lines member to point to the new buffer, and we update capacity to represent the new capacity, and we return 1 indicating success. Okay, so that's increase capacity or grow capacity. We have another helper method on text file called add line. So here we take the text file object, pointer to a text file object, and we take a pointer to a null terminated string on the heap. So this is a pointer that might be returned by our read line function. So here we determine if we're going to have to increase the capacity. If the size of our array is equal to the capacity of the array, then we know that the array is full and we have to grow its capacity. So that's what we do. We call our grow capacity function. If that failed, we return 0, indicating an error because we can't add our new line. If it succeeded, then we know that our capacity is now greater than our size, and so we store the line after the last existing pointer. We add our line to the array, and we increment the size afterwards. And then we return 1, indicating success. So now we've added 1 more pointer to our array. Now, the implication here is that the text file object now owns that pointer. So we've transferred ownership from the caller to the text file object. So here, now we have our text file. Here's another helper function called text file read file. So now we're going to read an entire file and add each line of text to our text file object. So we have a local variable called line, and we repeatedly, in our loop, we call read line. For each iteration of the loop, we call read line, store the result in our line pointer. If that result is not null, then we know we've successfully read a line of text. So then we call our text file add line function. If that succeeds, then it's implied that that line that that line pointer is now owned by the text file object. Because remember, the text file destroy function is eventually going to free that pointer for us when we delete the entire text file. So now we are no longer responsible for freeing that pointer. The pointer will be freed when the text file is destroyed. However, if text file add line failed by returning 0, it means that we did not successfully add the pointer to the text file. So now we are responsible for cleaning up by freeing the pointer. And then we return error to indicate to the caller that, in fact, we failed to read the file. So eventually, readline is going to return null, either because of an error or because we reached the end of the file. If we return an error if we have not reached the end of the file, it means that we failed to read the whole file. So we return 0. If we have reached the end of the file, we fall through to here, and that means we successfully read the whole file. We return 1. So here's main. Here's our main function. I've just specified a hard-coded a file path for demonstration purposes. Here we have our text file object. So we've created a text file object on the stack as an automatic variable. And here is our file object. This is a C standard library structure that represents an open stream, which could be a file, could be standard input, standard output, what have you. We call the fopen function to open the file. This returns a pointer to the open file. RT here is the mode. It means we're reading in text mode. If we fail to open the file, fopen will return null, so we just output a message and return. Then we call our text file initialize function to initialize our text file structure to a default empty state. And then we call our text file read file function to read the entire file. And so now our text file object should point to an array of strings, or point to an array of pointers, each of which points to a null terminated string. If that's succeeded, if the return value is non-zero, then we have a for loop here to just output each line just to do something with it for demonstration purposes. We iterate over all the pointers and output them each to standard output. If on the other hand text file read file return false, we just output an error message. And finally, at the end of main, we close our input file, and then we call text file destroy, which we already looked at, to free everything. So again, this is kind of demonstrating this concept. An important concept here is the concept of ownership. So it's ownership basically is a way of expressing the idea of who is responsible for freeing resources. So the read line function has a concept of ownership, which is that the caller is responsible for freeing the return pointer. And the text file struct has its own concept of ownership, which means that the structure itself, in a sense, owns both the array itself that lines points to, and owns each of the strings that the array points to. So that whole kind of tree of objects, if you will, is owned by the text file object. So whoever creates the text file object is responsible for calling text file initialize to set it to a default state, and for eventually calling text file destroy, which will free all the resources that are associated with that object. So that's the concept of ownership. So as long as you're doing kind of manual memory management like this, you have to deal with ownership. All right, finally, I'm going to show you an equivalent program that does the same thing as the last one, but written in C++. So you notice that the main function is now called main.cpp. So that extension indicates to the compiler that this is a C++ rather than a C file. So at the top of the file, we again have include statements. These pull in standard library headers. Now C++ programs can also use all the C headers, but the header files that with the the ++ part of the functionality all have names that don't have a .h after them. They don't have an extension. So we just have string, vector, iostream, and fstream. Those are the headers used in this particular program. So we enter our main function, and this whole program now is essentially equivalent to the one that we just showed you in C. So this really leverages the concept of ownership and how it is used in C++ to ensure that things are properly cleaned up. Because C++ adds a little bit more direct language support to things that in C are more just a convention that are up to the programmer to enforce. So you may remember from the last example that we had a couple of functions. We had this text file structure, and we had a couple of functions called text file initialize and text file destroy. And the text file destroy function, excuse me, this text file initialize function was called explicitly in order to put the structure into a valid default state, valid initial state. And the text file destroy function was called explicitly in order to free all the resources associated with that structure. In C++, so in C, that is just a possible convention you can follow. In C++, there is direct language support for this concept of having special initializer and destruction functions. And these functions are called, they have special names, and they're called constructors and destructors. And in general, in C++, there's this notion, there's this methodology, which has kind of given the clunky name RAII, which stands for Resource Acquisition is Initialization. And what that really means is that, another way of thinking of that is that resources are owned by objects. So acquiring resources occurs when you initialize an object, and then releasing those resources occurs when you destroy an object. And classes, sort of the C++ equivalent of a struct, is a class. Really, struct and class are almost interchangeable in C++, those keywords. But classes are basically structures that have some additional smarts, which is that they can have member functions as well as member variables, but they also can have these special functions that get called automatically by the compiler. So the constructor functions are automatically invoked when an object is created, and destructors are automatically invoked when an object is destroyed, and that allows this cleanup to occur automatically. And importantly, that happens no matter whether the object is destroyed. Like if it's a heap-based object, it might be destroyed by deleting it, by freeing it from the heap. But if it's a stack-based object, it occurs when you pass out of scope, and that occurs whether you pass out of scope through the normal flow of execution or whether you pass out of scope because an exception has been thrown and you're leaving the scope through an exception unwind. Okay, so in this function we use a couple of standard classes. We haven't in this function I haven't written any constructors or destructors myself, but I'm using a couple of standard class templates that do have destructors. So one of these is the vector class template. Template is also something that is in C++ but not in C. This is a way of you can write a class and parameterize it so that you can just write the vector class once, but then be able to create a vector of some particular type, in this case a vector of strings. So here I'm using a string class, which is part of the C++ standard library. The std colon just means that is part of that library. It's in this standard namespace. So the string class essentially is analogous to our pointer to an array of characters that we had in our C example. But in this case, we have a string object that owns that array of characters and also keeps track of its size and so on. Then we have a vector class, which is analogous to our array of pointers. Although in this case, it's actually an array of string objects. And the vector object allocates the storage for its array of objects, and it can reallocate them, so it can grow them over time. And it's responsible for ensuring in its destructor that that array gets cleaned up properly, including invoking the destructors on the actual objects in the array. So finally, we have, instead of calling fopen and fclose, C++ also has objects to represent streams or files. In this case, ifstream. Stream is kind of something you can read from or write to. An iStream is a stream you can read from. ifstream specifically is a stream that is implemented as a file. So when we construct the ifstream by passing a file path to it, it opens the file and puts the stream in a state in an open state if the file, in fact, it can be opened. So here we have a text file vector of strings that's been default initialized, and we have an input object is an IF stream that has been initialized by opening this text file. And then we have another string that we just use to hold the current, whatever the current line of text is. So this is just a string object. And again, these are all objects in a standard library so a string object owns a heap allocated array of characters that you can, I can add characters to it. It can grow over time. It can shrink, whatever. Then we have a function called getLine, which is actually in the string header file. And this will read a single line of text from the input stream and store that line of text in the line variable. So this variable is a reference. So C++ has this concept of references. So it's basically we're passing this line by reference. We're passing its address. And it's going to modify the line to include whatever the text is read. The return value of getLine is just the stream that you passed in, and that stream will be in a state that depends on the result of the read. So if we successfully read the line, then that state will be convertible to true. So we will to a true Boolean value. So we'll enter the body of the loop, and here is where we add the string to our vector. So we have our line is now the string that contains the line we just read. We call pushback to add that string to the vector. So appending an object to the end of the vector, we call it, the method to do that is called pushback. And this little extra std_move thing is kind of optional, but what that does is it specifies that the pushback method is allowed to take ownership. It's allowed to modify. We're using move semantics, which means that instead of making a copy of the string, we can move the string into the vector, which means that the pushback member is essentially allowed to transfer ownership of that pointer to the object in the vector and clear the string that we passed in. So we add the string to the vector, and then we go and read the next line, and we keep doing that until the stream is in a state where that converts to false, which could happen either because we've reached the end of the file or because it's in some sort of error state. If we reach the end of the file, then we reach this part of the code, and we just iterate over all of the objects in the vector. This uses what's called a ranged for loop. This is like a for each object. It's like a for each loop in C#, for example. So using this colon syntax means that for each element in this collection in the vector, we will initialize line will be a reference to whatever type the object is. So auto means that we can derive the type. We can let the compiler deduce the type for us. So it's going to be an std string, in this case, a reference to an std string. And then we output the string. And instead of using printf in C++, C++ has its own methods to write to the console. So we can write the line followed by a new line character. And finally, and then if we have not reached the end of the file, it means that some error occurred, and so we output an error message. So cout will write to the standard output. Cerr will write to the standard error output. Finally, you notice that we haven't done any null checks here. If something happens inside any of these methods like getLine or pushback where it has to allocate memory but fails to do so, instead of returning a null value or something like that, it will throw the way of handling that in C++ is typically to throw an exception. So if that exception is thrown, then any objects then the stack will unwind until it reaches a catch block. Any objects that passed out of scope as a result of that stack online are properly cleaned up. And then we reach this catch block, which will then output an error message saying we're out of memory. So that's how out of memory will be handled in this particular program. So this kind of illustrates how, one of the burdens of, so C supports this dynamic memory allocation through pointers, and just with very limited language support. It's very capable. You can do anything in it, but it requires, the burden is on the programmer to determine how you're going to ensure that things are cleaned up properly, how errors are handled correctly, and all that kind of stuff. This is all doable, but it requires, the language is not very opinionated about how you're going to do it, and the language doesn't provide any guarantees that you're going to do it correctly. It's really up to you to adopt some conventions and follow those conventions rigorously. C++, so other languages have their own ways of simplifying this task for you and taking the onus off the programmer. C++'s approach is to use this RAII idea where objects own resources, and also C++ provides a lot of standard classes that use that to do things like smart pointers and containers and so on, that own resources for you and handle that cleanup automatically by invoking the destructors. Also, C++ uses exceptions to allow you to avoid having to write as much error handling code, or at least the error handling code doesn't have to be sprinkled throughout your code. It can be relegated to catch blocks, but it does require that you program in a way that is exception safe, which essentially means that if you want things to be cleaned up properly, since you have to make sure that you kind of rigorously follow this RAII model, because otherwise you're not necessarily going to have an opportunity to do cleanup if an exception occurs. As long as you follow the RAII model, where objects own resources, then cleanup will occur, even in the case of an exception, because the objects do the cleanup when they're destroyed. So that is the C++ approach. Of course, other languages adopt different approaches. In C# and Java, for example, heap allocated objects are always going to be cleaned up through garbage collection. This means that instead of explicitly having to call free to free memory, every so often the runtime environment will sort of pause execution and look at all the variables on your stack and follow all the pointers, follow all the references that occur, and figure out which heap objects are still reachable by, still have references to them directly or indirectly from anything on any stack of any thread. And if they are, fine, they're kept alive, and if they're not, they can be cleaned up. So this involves a little bit of runtime overhead whenever the stack is paused. Garbage collectors are actually pretty smart, but it does mean that the cleanup does not happen at a deterministic time. It happens when the garbage collector happens to kick in and run. For certain kinds of resource management, like not all resources are just memory. You can have things, for example, like an open file, and maybe you do want the cleanup to happen at a deterministic time. You don't want to hold a lock on that file or hold a lock on a database query or something like that until you just want to hold the lock and then immediately release it. For those kinds of things, C# has a using statement, which is a special kind of logic in order to ensure that things that are usable, or what is the term for it in C#? I forget. Disposable, things that implement the iDisposable interface. There's a pattern for disposing of objects when you leave a block of code that is a specific kind of block, a using block. So there's a pattern for that kind of resource ownership, but it's a little bit more explicit. Whereas in C++, the model of resource ownership is a little more complicated to grok in some ways, but it also is very generalizable because it applies to all kinds of resources, not just memory. Okay, so that kind of gives you an idea of how object lifetime works with pointers and how different languages approach it. The pitfalls of object lifetime are that you can end up, if in a language like C, where you're just dealing with raw pointers and the lifetime of the object is the language doesn't enforce any kind of guarantees as far as how the lifetime of the pointer corresponds to the lifetime of the object. You can end up with situations where you have a dangling pointer, where you have a pointer, but the thing it points to no longer exists. And that can lead to undefined behavior. And we've seen how that can happen with um, with automatic variables, where you return a pointer from a function, and that pointer points to an automatic variable that went out of scope when you left that function. I haven't shown an example, but the same thing can happen for heap allocated objects. You might have more than one pointer to the same heap object, and maybe you delete the object through one of those pointers, and then somebody else tries to use the other pointer, and that object is already gone. Or maybe you try to free the object through both of those pointers. That's a double free. That's also illegal. So object lifetime requires some discipline to ensure that that when you work with pointers, you have to use some discipline to ensure that objects live as long as they're needed and no longer, but also that you don't try to use objects through pointers that don't exist anymore. In C, it's really just up to you to use some sort of conventions to get it right. In C++, the language is a little bit more opinionated. There are conventions that have direct language support that make it easier to do this in a less error-prone way, and in particular by instead of doing manual resource management, by using classes that are in the standard library that handle the resource management for you. And of course, in other languages like C# or Java, most of this lifetime is handled by the language itself or by the runtime environment through the mechanism of garbage collection. All right, so I hope that was instructive, gives you a better idea of what the issues with pointers are, but also kind of how memory really works under the hood. How you can have things allocated on the heap and that can point to other things allocated on the heap and so on. And that anytime you have stuff allocated on the heap, you have to deal with you have to worry about object lifetime. Thanks for watching. Bye.